So I think we can start. So hello everybody. This is Luboš Pirkl and Radek Maca from CFD Support. Welcome to the webinar on Turbomachinery CFD, which is a universal workflow for simulating all standard rotating machinery. Turbomachinery CFD is smart and easy and affordable CFD software. And in today's webinar, we would like to show you a little bit about it. So I hope everything is working now. Anyway, in case of any technical problems, feel free to contact us in the future and we will gladly answer all your questions and reminders. The test case, which will be part of our webinar today, will be an Axial fan. And so I think we can slowly start. So let me introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support. And today I'm sitting here with my colleague, Radek Maca. Hello, Radek.
Hello, Radek. Hello, everybody.
So how are you today?
Yeah, I'm fine. I'm really fine today. So.
Okay, and so are you ready for the webinar?
Yeah, I'm ready. It's never before. So please.
Okay, very well. It's great to hear this. So let's go ahead. So I will only notice Radek is our head engineer and he's a senior developer here at CFD Support. Radek is great mind of today's times. He's living legend of CFD engineering. So I believe it will be a great time with him today. So okay. So let's start. So I will switch my camera off and also Radek. So let's switch it off, and let's continue with our presentation. So about the webinar, so the webinar is going to take up to 1 hour, depending on the number of your questions and reminders. There will be 3 parts in this webinar. In the first part, I will give a general introduction to Turbomachinery CFD. I'm going to point out the main Turbomachinery CFD features and benefits. In the second part, there will be a live example where Radek is going to show you how to simulate an axial fan in Turbomachinery CFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window, or you can even send us your questions by an email to info@cfdsupport.com, and we will answer your questions later in this webinar. Especially in the beginning of this webinar, we are gonna be quite general, but feel free to put your questions in details, and we will gladly provide all the information. About the CFD Support, so CFD Support is a private engineering company located in Czech Republic, in Prague. We deal mainly with computational fluid dynamics. We are used to deliver complete CFD engineering projects on demand all across the CFD field. We do also quite a lot of outsourcing. We deliver extensive open-form training and consultancy, as well as we deliver lots of open-form support and custom development. But of course, that's why we are today here. Our flagship product is a software which is called Turbomachinery CFD, which brings me to Turbomachinery CFD. So please let me give a brief description of what is Turbomachinery CFD. So Turbomachinery CFD is unique software based on OpenFOAM. It was designed for CFD simulations of all standard rotating machinery, such as pumps, fans, compressors, turbines, water turbines, both radial and axial machines, both compressible and incompressible fluid flows. Turbomachinery CFD is complete CFD workflow that covers all the engineering steps from the preprocessing over the simulation run to the very detailed post-processing of the results. It's independent on any other software, and on the other hand, it's fully compatible with standard OpenFOAM, so we believe it's very comprehensive and it gives all the features which are needed by today's engineers. Let me put just a quick review of its unique value proposal. We believe Turbomachinery CFD is unique at least for 4 reasons. Number 1 would be Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. This gives the investment in Turbomachinery CFD a permanent value. And also this means our clients can scale their Turbomachinery CFD simulations in a big way because it's fully unlimited. Number 2 would be Turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final results report, it can be run by a single click or by a single command in command line. And all the process is being done automatically. It's fully automated. So for this reason, Turbomachinery CFD is extremely effective because it's really effective. It produces the reliable and accurate results. Number 3 would be we deliver extraordinary technical support we are proud of. We keep custom approach to every customer, to every issue. We are very flexible in it. We never leave behind any of our clients. We support our clients even in matters out of the turbomachinery field. For example, in numerical mathematics, physics, CFD, IT, or even software engineering. So the technical support is very extensive. Yeah, and number 4 would be, so in Turbomachinery CFD, the real tutorials are included. So the Turbomachinery CFD has no doubts about the best practice settings. There are included the preset real machines that are working. So you basically take one of those tutorials, replace the geometry with your own, you modify the physical settings and run the simulation. So it's ready to use. That's the final point. So these are. This is the unique value proposal. Of course, there are many other benefits of using Turbomachinery CFD. I'm not going to go for all of them right now. Okay, so I will go ahead in my presentation. So Turbomachinery CFD. There are also some details, so I will quickly mention Turbomachinery CFD is available both for Linux and Windows operation system, and by the way, today's webinar will be organized in Windows operation system. The Linux workflow is very the same or exactly the same as in Windows, so it's always your choice, it's always our client's choice which operation system they choose. Turbomachinery CFD is fully served from graphical interface. So graphical interface for Turbomachinery CFD is the ParaView. You can also work from a terminal, but most of people prefer to work from the graphical interface. Of course, Turbomachinery CFD can be also run on clusters and clouds to scale your CFD simulations in a big way. The decision is always up to you. The workflow can be additionally scripted because you can add any features by yourself. You can connect to Turbomachinery CFD. You can edit it in your way. You can modify it to your workflow you are used to use. Turbomachinery CFD is transparent, so the trial version, the demo version, is available for free for 1 month period, so anybody can try Turbomachinery CFD, and afterwards he or she can decide to go for it or not. So it's very transparent. The demo is available, and you can decide after you try. The real tutorials are included. Every single simulation has its detailed report in web responsive HTML format. It's extremely effective tool to have automated reporting. So you see immediately during the simulation what are your results, what are your main integral results, what are the features of your machine. It's very effective. Also, there is included a special post-processing tool which is called TurboBlade Post, which enables special post-processing in the visual way. And it's a special set of plugins for ParaView where you can do the averages for Turbomachinery and also blade-to-blade view and many others. And finally, yeah, also the Turbomachinery CFD includes CFD processor, which is a special software tool for automating of the OpenFOAM cases. Yeah, and finally, and perhaps the most important information from today's webinar is all the information is available online on our website. So you can go to our website to CFD support, Turbomachinery CFD, and you can get the information from there. I think this is it for now. It's time for the live example. So today's live example will be an Axial fan. So Radek, may I ask you, are you ready to show the audience the workflow with software?
Yes, I am. So please give me the presentation.
Okay, so I will switch to you. So I'm right now making Radek the organizer.
Okay, so I hope you see my desktop.
Yes, yeah, it's perfect.
Perfect.
It's perfect.
So hello again, this is Radek Maca speaking, and because Luboš had already said many general information about our software, about our company, so I will directly jump into the practical part of today's webinar. So I guess it's good to start with a few information how to physically start working with our software. So basically, a lot of information you can find on our web pages. So what you have to do as a first step to start working with Turbomachinery CFD is to download OpenFOAM. We have, as Luboš has already said, we provide both versions for Windows and for Linux. So today I am in Windows, so I will use the Windows version of our OpenFOAM inbox. So to download it, just go to our web pages, to the product part, go to the OpenFOAM for Windows, and here is the download OpenFOAM for Windows. Here you just fill in the form, you just fill in your email address and click on download, and the installation process is very straightforward. Afterwards, you should ask for a trial version of our Turbomachinery CFD. So you can go to the product again, to the Turbomachinery CFD, and here is the Turbomachinery CFD trial version. Click here and you can fill this form and send the request, and we will immediately send you a trial version of our Turbomachinery CFD, which is valid for 1 month. So you can use it, you can test it by your own on your computer on your site. And the last thing is to download today's case, which is Axial Fun. So simply again click on it, type your email address. So I will do this, and click on download button, and you will download today's case. So I will jump to my favorite file commander, and yeah, I'm in download section, download directory. Here I have Axial fan tutorial, and I will copy it to working directory of OpenFOAM of Turbomachinery CFD, which is installed at the C drive in OpenFOAM directory. You will use the current version of OpenFOAM for Windows, and here I have my home folder and in the run directory. So I will copy today's case. Okay, so what is the input of our software? It's just simply, you can see the directory with STL. So it is a directory with a geometry which defines the axial fan. So it is split into several parts which together create the geometry for axial fan. And here are the axial fan CFD, which is our configuration file. So if I open it, you will see there are several parameters by which you define your simulation, by which you define your case. So there are several options how to set up. So the direct way is to edit just this file and run the simulation directly from console. So by to do this, just click on the Turbomachinery open for Windows. You will open our new console will open, and I will simply jump to my axial fan case, and the simulation can be directly run by CFD processor, which is a tool which manages all workflow of computation fluid dynamics of CFD at one click. So it creates the mesh, it set up the case, it runs the case, and it post-process the case, and it also creates a report in which you can see efficiencies, pressures, and so on. We will see in few minutes. So the usage is really simple. Here is the help, and to run all by one click, you just type CFD processor. With the option setup, you should define the configuration file. So it's Axial -fan.pcfd. Then you can define your own name of the directory, for example, my case, and by flag or run, which is here, combines everything. So it writes the case, the OpenFOAM case, it creates the mesh, it calculates it, and creates the reports. So by this command, or run L. So it runs all the workflow, and in several minutes you will see the results. So this is, for example, useful to run the simulation on some cluster using just a console, just one command. But more effective way is to use graphical user interface. So I can go, for example, back to my file commander, and just by clicking on the axial fan configuration file, it will directly open the ParaView, which is standard third-party software which is connected to OpenFOAM and can be used for visualization of scientific data. And we have developed the graphical user interface directly in this software. And by clicking on the configuration file, it automatically opens so-called PCFD source, which is a plugin by which you can set up all important parameters to run the case using our Turbomachinery CFD. So now we can go step by step and just tell or just discuss the parameters which can be set up within this graphical user interface. So in the general setting, you can load your preset TCFD file, or you can just start from scratch and start filling really the new case to run. The machine type, our software provides say 5 standard machine types. Start with compressors, fan, pump, turbine, and water turbine. So you can choose which one you would like to simulate. Then you simply, in the coordinates part, you will define the origin and the axis, which belongs to usually to the axis of rotation of your machine. In the geometry, you can input your geometry, for example, in millimeters, like in this case. So if you, because OpenFOAM implicitly works with the meters, so you should scale it to the meters. And anyway, every time you point to the button to the box, you will see the help. So it is useful feature. So you can read by which parameter you can set, or how to set each parameter. In the physics, you can define gravitational acceleration. You can choose your fluid type. If it's air, implicitly for the preset, fluids are air and water. But anyway, you can change the dynamic viscosity because we solve this axial fan because there is small pressure drop. So we will solve in incompressible mode. So you should preset, or you should define the reference density, reference pressure, and reference temperature. Usually it is used to recompute the pressure in Pascal units, and it is used also to evaluate the efficiency. Another part is turbulence modeling. So we can basically use laminar, so no turbulence model, and or K omega SST or K epsilon model. What I didn't say that here is the advanced button. So if you click on it, you can set directly here all parameters which is connected to each turbulence model. Yeah, so you can change it. You can change it to your purposes. So by this clicking on this advanced button. Next point is to define the computing points, the working points of your machine. So here you set the rotational speed. You can generate directly more speed lines. So for example, 2 or 3 with different rotational speeds. For each speed line, you can define working points, so points with different boundary condition, usually points with different flow rates or with different pressure drops, with different initial pressure conditions at the outlet or at the inlet. And for each point, you will define maximum iteration to be computed. Next section, define the inlet and outlet boundary conditions. So for the axial fan, we define the volumetric flow rate at the inlet. Of course, our software provides another initial inlet and outlet boundary condition. So in this case, defines volumetric flow rate. Of course, at the beginning, if you are using turbulence model, you should define turbulence quantities at the inlet and at the outlet. For this case, we define fixed pressure. We define 0 because the incompressible mode works with kinematic pressures, so it is a standard approach for setting pressure for incompressible cases. Next one is the simulation part. So here you can define, or you can compute your cases in steady state mode or in the steady state plus transient. So also our software provides transient simulations. Here you define how many processor, how many cores would you like to use for the computation, and use some advanced parameters. And so it's the maximum and minimum pressure which you allow in your simulation. The same holds for the velocity. The next point, you can choose between first and second numerical order, and you can enable automatic convergence check. So it means the computation checks some conditions, which, if this condition, it means if the simulation is converged, if the efficiency is converged, so it can stops the simulation before the maximum iteration is reached. The next section is the numerics, and here are the relaxation factors which makes the solver more robust, and it deletes some oscillations in solution and so on. Well, another part is the initial conditions, so it's just the initial guess from which the computation is started. Initial pressure, initial velocity, initial turbulence quantities. And now we are coming to the important part, which is the setup of the geometry and setup of the mesh. So here in this case, by double clicking, you can see here the topology of your mesh. So we say two components. So first is the impeller, so the rotating part, and the stator part. So anytime you change something or you would like to apply your settings, you should click on apply. And if you set the geometry, you will directly see what is the input geometry for your case. So you can see that the red part is the stator part, and the white part is the rotor impeller part. How to define geometry? So as I said, this geometry, this case uses the STL files. So in here, you just define the directory where the input geometry is saved. So in my case, it's the STL, and our software also provides to read some external mesh, which is converted to OpenFOAM. So in this case, you can choose here external OpenFOAM mesh. Well, you can create a name, custom name for each component. So here is the impeller. Our software provides also periodic segments, so you can just simulate one segment, one blade, if you input this type of geometry. And what is important, for each part of the geometry, you should define the boundary type, the patch type, so-called in OpenFOAM language. So here is the impeller. So for example, it is really simple and straightforward. Impeller blades has type blade, hub has type hub, the inflow part, so the entrance to the domain, let's say, is the inlet, and the interface, which is connected to another part of your geometry, so to another component in our language, it is outlet and inlet interface. So on this type of patches, the special boundary condition is applied, and the communication between these components are satisfied. Well, and of course, you should define which part of your geometry is rotating, and in general, which component is rotating. So you can check it by this option rotating component. This leading edge gap, trailing edge gap, and blade gap. So it is the distances. So it can happen, or to make the machine process more robust, you can define some small gaps in your geometry. Gaps, I mean the small, tiny places between two different pitches. So if you define the exact distance, so the machine process can make mesh finer in these places. What is the next? Next is the size of your background mesh. So it means it's the largest cell in your geometry. So in here is defined 30 millimeters. Internal point, you should define the point which the point in the geometry, so the place which should be meshed. So usually it means if you would like to mesh inside or outside part of your geometry. And for example, for axial fan, it is useful to know wheel diameter because it is used in some post-processing utilities. Well, because the meshing or the meshing process is managed by SnappyX Mesh. So using these setup parts, you can define all parameters in SnappyX Mesh. But anyway, it is for each machine it is set up with best practice. So at the first touch, there is no need to change anything in these parts. But for some advanced simulation, you can play with the parameter here. Another useful thing is the post-processing. So implicitly, the efficiency, the pressure drops are evaluated from inlet patch and from the outlet patch. It means the physical inlet and outlets in the geometry or out of the geometry. But if you would like to just evaluate, for example, efficiency of the rotor part, you will just add new efficiency probe, and you will just define the impeller inflow for inlet patches. You will define which parts of your geometry will be included in the torque computation. So let's say all the parts or just hub and blades, and of course outlet. So outlet of the rotor part, so impeller outflow. Okay, and now for this setup, we will see at the end of the computation also the efficiency just for the rotor or for the impeller part of the geometry. And another useful point, another useful tool is the scripting. So you can use a simple script, simple Python script with some preset function to change anything in the case. So for example, you can, I don't know, add some your own utility or some advanced post-processing tool which is prepared for your particular case and so on. So the doors is not closed for some modification and non-standard optimization or evaluation of your geometry. Okay, so this is it. So we went through all these parameters. So don't remember to, at the end of your setup, don't remember to apply, to click on the apply button to save your setup. And so this basically creates the Turbomachinery CFD files. You can anytime save it, yes, or reload it or load some new one. So this creates Turbomachinery CFD. And for example, if you save it, and you can run it directly from console, or you can use another filter which is called CFD Manager, which can be applied to the settings, and the simulation. Each step of simulation can be directly manage also from this graphical user interface. Okay, so I will close this component button, the component window. Okay, so basically, at first you should save the case, and you can define some custom directory name. Again, for example, my webinar case. Okay, so I should click apply button and then write case. So it write the OpenFOAM case. So now it is saving the geometry to the OpenFOAM case. It is somehow checking the geometry if it is correctly defined. And now you can see here my new webinar case and standard topology of OpenFOAM case. Afterwards, the meshing process is waiting for us. So basically, you can build each component, it means impeller, stator, by one click, or you can mesh all components at once. Afterwards, the mesh is done. You can run the calculation, and here you will see the calculation process. You will see how long does it take to finish the simulation. You can jump in, you can skip to the next point, and of course you can abort the calculation. And anytime during the computation, you can update the report, which I visualize in a few moments. And also you can run all these steps at one click by clicking on the run all. So it just first creates the mesh, then run the calculation, and at the end of the calculation, it creates the report. And during the computation process or meshing process, you will see what is happening directly here. So at the end, so I will make a time jump. I will make a jump in time, and yeah, here. So okay, this is at the end of the simulation, and you will see this report. By the way, you can see anytime during the simulation by clicking on this update report button. So what information are included here? So of course the name of your directory, basic simulation statistics. So how many points was simulated, type of machine, rotation speed, basic information about the mesh, details, some face area. So all standard information about the mesh are included here. Y plus parameter, which is important for turbulence modeling, the time of the computation, how many processor was used for the computation, and if the compressible mode was enabled or not. Then, for example, for fun, the typical parameter is the fun characteristic, which is the plot between just phi value between psi, as compressibility coefficient with respect to the flow coefficient. Of course, efficiency for each point of the simulation. So you can see the value part, so the list of the values for each simulated point. You can see the graph, and also you can see the convergence process of efficiency. The next part defines the torque. Again, the list of torques for each point, the figure of torque with respect to all the points which were simulated, and again the convergence process. And the same topology is for another variable. Here is the total pressure difference between inlet and outlet. Total pressure per each interface, so it means total pressure at inlet, at the interface between components, and the outlet from the geometry. Next one is velocity magnitude per interfaces. circumferential and meridional angle at each interface. And yes, this is all. So it's a really comprehensive report, and you can read directly all the important parameters for your simulation. So this is, let's say, some this is post-processing, and this is report which can tell you parameters and what you can do more. So for some visualization, and to post-process the cases, directly in ParaView, and to see some velocity gradients or pressure gradients directly at your geometry. So I will go to my computed case, Excel fun computed, yes, to my webinar case, okay, and here by clicking on the case form, I will open standard ParaView with my computed case automatically, and if I click on apply, and here is the check implicitly internal mesh, but I can visualize any part of the geometry. I can go to, let's say, to the point number 10, to simulation point number 10, and here you can see, for example, the pressure distribution on your geometry. We implemented some nice filters, and I will present you right now. So first one is the meridional average. So basically it projects all okay, so basically this is our input geometry, and if I apply this meridional average filter, so it creates a virtual plane. It cut your geometry at the given part, and it projects the meridional average of your whole geometry. So it means at the end you will see the distribution, the average distribution for the total pressure for as an example, and the setup is really straightforward. The meridional average has just 3 parameters. So you should define the axis of the rotation by defining a vector axis, a vector of the axis, and a point on this axis. So means origin, and the resolution of this virtual raster. So I can visualize it, for example. So the largest side of this virtual plane has 100 cells. On this raster, all the variables from pressure to some turbulence quantities is averaged, is meridional average, and visualized at this plane. So this is the first useful and nice tool which we had developed, and the second one is Turbo Unwrap. So it is simply again applied on standard case file, and the Turbo Unwrap again defines just few parameters: the axis of rotation and origin. Break means the direction in which the wheel is cutted and unwrapped, and what part of the domain you should visualize. So this first window defines what part of the mesh to unwrap. So for me it's now internal mesh, and parts which define hub and shroud. So in my case, impeller hub and impeller shroud. If I apply this filter on my case, you can see. So originally you see something like this. So unwrapped wheel. And what is really nice that the new coordinates, which which is in the Z direction in my screen, corresponds to the radial coordinates, the relative radial coordinate of the full wheel. So if I apply, so this is just the mesh, and if I apply the slice on this unwrapped mesh with Z coordinates equal to 0.5, so it just visualize the slice which corresponds to the radial coordinate. Let's say it corresponds to the slice which lies directly in the middle between the hub and shroud. And on this slice, you can visualize, for example, streamlines using these surface LIC, and you can nicely see, and you can nicely post-process, and you can directly view the streamlines along your blades at the given radial coordinates. The similar thing can be just applied not to the internal mesh, but just for your blades to see the pressure, for example, pressure distribution on the blades of your machine. Okay, so I guess, yeah. Okay, so I guess I am at the end of my part. So I will give the presentation back to Bosch.
Okay, very well. Okay. So thank you. Okay, thank you, Radek. So I will show my screen. So I believe you can see what I see, which is the original part of my presentation. So thank you again, Radek, for your live example demo. And I will quickly finish my presentation. Before I do that, I would like to kindly ask you to give your questions. Just take your chance. It's your time. We are here for you. So we are ready to serve. So feel free to put your questions, and we will gladly answer it. I'm gonna finish with how to get Turbomachinery CFD. So Turbomachinery CFD is transparent project. So the trial version, the demo version is available. Anyone can try Turbomachinery CFD full version for 1 month and decide to take the action or not just after that. The paid version is always perpetual, so you can keep it for forever. What is paid for? This is really important. So at Turbomachinery CFD, what is paid for is the fast delivery and technical support, updates, and maintenance. This is really important. So what is paid for is the fast delivery, technical support, and updates, and the maintenance. We believe Turbomachinery CFD is very affordable. We decided to fight hard for the universities. So universities pay only 3,000 euros for the delivery and first year of technical support, updates, and maintenance. And private companies pay 12,000 euros for the delivery and the year of technical support and the updates. But I just repeat, you can keep Turbomachinery CFD in the full version for forever, and you can use it for unlimited number of users, jobs, or cores. The important thing is what you pay for is the technical support. So after the year, you can decide not to go ahead with us. We can split, and you can continue on your own, and you can keep everything for the ages, and of course you can get back anytime. So we are very flexible in this. And yeah, I just leave it with please contact us for more details, and we will gladly answer it. Which brings me to the last stage of our webinar. It's the Q&A. So I would like to really ask you to put your questions, and we're going to answer them right now. So Radek, what questions we have?
Okay, I will start. So I see directly here's a question, why streamline is used. So I will answer it. So I will I will, I will take the presentation. Okay.
Okay,
Perfect.
you're welcome.
Yeah, it was just an example what can be visualized directly in Paraview using our filter Turbo Unwrap. So it's just an example how to visualize streamlines on some radial slice. So what can be used for? So you can see directly if the angle of attack is okay, is correct. If you can, for example, see some wakes. If, for example, the setup, let's say, if you set the rotation speed on really high value, so you will see that there is big recirculation area uh, in the neighborhood of your blade. So it is a tool how to see directly visualization of the flow of your computation. Yeah, it was just an example. So you can just, for example, visualize pressure or, okay, I have here, for example, velocities, the velocities magnitude, and so on. Yeah, so, oh, it's too much. So it was just an example, and it can serve as a nice visualization tool of your simulation. Yeah, so there was no direct let's say, yeah, it was just an example. So who would like to visualize this? It is the possibility. Who don't want to, okay, it is not necessary. So I hope it was answered, or if not,
Okay.
please answer your next question.
Okay, so Pavitra is asking, can we import mesh directly from other tools? So Radek, would you answer this?
Well, I don't know what is the meaning of the directly, but anyway, any software has its own mesh, let's say, or the format of the meshing and so on. But OpenFOAM provides utilities to convert the mesh from, I don't know, from the ANSYS meshing, from the Numeka or etc. So directly means, if the directly means that using utility which can convert the external mesh from the Numeka, for example, to OpenFOAM, and then directly this mesh can be loaded to our software. So, but there is one step just to use utility, which is directly in OpenFOAM. So, one-click utility which can convert the mesh from some external meshing program to OpenFOAM, and then this can be directly used in our software. Yeah.
Okay, and Radek, can you show, because the answer is the answer is yes. Turbomachinery CFD can load external meshes, and Radek, can you show how would you do that?
Okay, I can. So here is the setting part. Back to the setting part, to the component setting, and here, because if you use this convert utility, it creates new OpenFOAM case, and this can be directly used. So first, sorry, here you check the external OpenFOAM mesh, and where is it? Here, the case path, you will just tell the directory where to find this converted mesh, and that is all. It will enable the original patches, and you will preset the types, rotation, what is rotating, and so on, and this mesh can be used for the simulation.
Okay. Thank you, Radek, for this. So yes, so Turbomachinery CFD can use the external meshes. Okay, so I will just take a look. Yeah, I have to say I can't see any more questions, so maybe I can just tell you we have some time still remaining, so I can just tell one of typical questions we are used to receive. So, for example, many people ask whether Turbomachinery CFD can design the designs of the machines, or or not. So the answer is no, it can't. So you need to have your design tool for this, and Turbomachinery CFD is just a simulation tool. Maybe what's quite important, okay, I'm back in my presentation. Maybe I can show you in my browser. If you type Turbomachinery CFD, the very first result is Turbomachinery CFD website, and from there you can get to the workflow example, and somewhere quite at the top you can see we have there the Turbomachinery CFD configuration file manual, and there you can see the multiple inputs to the configuration file and also its description. So this might be very useful for the engineers, because in this file you can learn what are the inputs, what are their dimensions, what are the other possibilities, what are the parameters, values. So this is very important file for the engineers. It's like a manual. It's very small, very brief, but the engineers, the experienced engineers understand easily what's the meaning of those parameters and their values, of course. So that's the tip for you. You can, for example, if you have your own design tool, you can easily export to Turbomachinery CFD format, because the format is clear, it's obvious to everybody. So the input is just a surface format and the configuration file, and that's it. So maybe this is what people are often asking for. I can see one more question from Pavitran. Is there any option to define a tip gap? Well,
I can answer.
Okay, Radek, yes, please.
Well, I will take him. Okay. So I hope I understand correctly. So if you would like to define the tip gap in the meaning that you would like to simulate some unshrouded case, so it means there will be gap between the shroud and the people part of the geometry. So this software works with the generated geometry. Yeah. So at this moment it doesn't change the geometry. So what is the input is also the output. So what geometry we define, it will be used, it will be automatically meshed and used for computation. So at this moment not, but for example we are in cooperation with the companies which is CF Turbo, and they have really nice software for designing machines, and directly in that software you can define this tip gap. So for the unshrouded case, and from this software it can be directly exported to our TCFD software and can be simulated with this tip gap. Yeah. So maybe I will go here. Where is it? The setting part. Yeah. So and for this type of geometry, there is the option for meshing. Okay, the input is STL, and where is it? Here you can define this black gap, and it means you can define this gap distance between the cap of the blade and the shroud, and it will correctly mesh this part. Yeah, but it doesn't mean that it changes this
Right.
shroud. Yeah.
I will only add that what's the input that's meshed and that works. So it allows computing in this we call them clearances. So it computes also the clearances because the machine is automated. So it computes the clearances and that it's a matter of the input. So this Turbomachinery CFD is just a simulation software. So it's a matter of the design tool. Okay, so I have to say I can't see any more questions. So I will put for a while I will put my camera on, and I think it's time to conclude. So we would like to thank you for your time, for your attention. It was a pleasure being here with you this afternoon, and yeah, so we are here for you. So we will gladly support you in anything. So feel free to contact us in the future. We will gladly answer everything. We are very transparent. We believe we are creating very strong and powerful software, which is smart, which is easy to use, which is very affordable. So we will be looking forward to meeting you somewhere someday. So Radek, what do you think?
Yeah, thank you for watching. It was a pleasure, to be here with you, and we are looking forward for future cooperation, for the future questions, and we are open for all problems. So do not hesitate to contact us if you have any problem.
Okay, so thank you for your attention. Stay tuned, and we will be here for you. So I think it's time to say goodbye. Okay, so bye.
Bye.
Yeah, bye. Okay. Yeah. Very well.